sometime in a not too long while. So, and I really hope that there's going to be plenty of questions. I heard that you are famous for open-ended discussions and grilling speakers, and I'm all for it. So I'm going to tell you about this work I've been doing with Apratim, who I think is attending this talk, and with Emilio Trevisani. So we've been working on this for a long time already, for a couple of years. And so this has to do with supersymmetry, Parisi-Sourlas supersymmetry, and the random field Ising model. And we have a paper out, and we have another paper in progress. Hopefully it will appear in a month or so. So without much ado, let me define the physical system that this is about. So the random field Ising model is a lattice system studied by statistical physicists. So we have a lattice in d dimensions, and on every side of this lattice we put an Ising spin. So the first part of the Hamiltonian is just the usual Ising model Hamiltonian, and then we couple these spins to magnetic fields, one magnetic field per side, Hi. And the particularity of this system is that this magnetic field is by itself a random variable. So it has its own random distribution, which, for example, can be chosen to be Gaussian, identical Gaussian distribution on each side and independent. So there is an average value 0 for this magnetic field, and magnetic fields on different sides are independent. And this magnetic field is supposed to be a quenched type of disorder, which means that when we compute observables in this lattice model, for example, spin-spin correlation function, what we are supposed to do is that we first pick a particular representative a magnetic field from this average ensemble, so this H. We keep it fixed. We compute this two-spin correlation function with this magnetic field, which means that we do the average and we divide by the partition function for this H. And then once we did this, we average over all possible H's. This is called quenched average. And in this setup, we are interested in several classical questions of statistical mechanics, such as what is the long distance behavior of such correlation functions as a function of the temperature and of the disorder strength. For example, is there a phase transition? Is there a phase transition as you vary the temperature, as you vary the disorder strength? And if there is a phase transition, what are the critical exponents for the correlation functions? And this has a physics motivation, because the real magnets described by the Ising model, they're never pure. They always have some sort of disorder. And there are two types of disorder that you can imagine. There is the random bond type of disorder, which amounts to adding some random perturbation to this coupling J in the spin-spin coupling J, but that's not what the type of disorder that I'm considering today. Today I'm focusing on this random field type disorder when you couple to the magnetic field. In fact, both types of disorder are interesting. The random bond one is easier, as I will comment why. And this random field type disorder is a big famous puzzle in statistical physics, as I will review. So any questions about the model? So if there are no questions, then let me go to the field theoretical description of this system. So I write a field theory. Supposing there is a field phase transition which is continuous, I can use the field theory. And in the field theory, I write, as for the Ising model, the usual scalar field action with quartic interactions. And I add this magnetic field, but now everything is continuous, depends on x, h of x, phi of x. And the first question that we'd like to know is whether this perturbation is relevant or irrelevant, perturbation of the Ising fixed point. For this, we have the so-called Harris criterion, which says that the disordered perturbation is relevant if the operator to which it couples has dimension less than d over 2. So compared to the usual relevance criterion for non-disordered coupling, we see that here d over 2 instead of d, which has to do with the fact that when you use this disordered coupling, you basically have to use it twice in order to get something non-vanishing, because the average value of h is 0. Only the second moments of h are non-zero. And but in any case, this criterion delta phi less than d over 2 is satisfied at the Ising fixed point in any dimension. And so this means that this perturbation is going to change the universality class. It's going to be relevant. So we need to know where this perturbation is going to flow. And about this, there's a famous conjecture made by Parisi-Sourlas in 1979, which has several parts and several formulations, but one formulation that is modern, that I'm going to use today, is that the first part says that the phase transition in presence of disorder is described by a superconformal field theory living in d dimensions. And the second part of the conjecture says that this superconformal field theory in d dimensions is in a certain sense equivalent or reduces. In particular, it has the same critical exponents as a non-supersymmetric conformal field theory, local non-supersymmetric conformal field theory living in d minus 2 dimensions. So 2 dimensions lower, and this is something which is called dimensional reduction. This CFT d minus 2, it has the same global symmetry. For example, the Ising model has Z2 global symmetry, so both of this SCFT and CFT will have Z2 global symmetry. And so if you put these two parts of the conjecture together, then you arrive at the conclusion that the random field Ising model in d dimensions should have the same critical exponents as the Ising model in d minus 2 dimensions. And this conjecture is a subtle conjecture, so it's actually not quite right, but it's also not quite wrong either. And so this is the puzzle. So in fact, the status of this conjecture is as follows. So first of all, it's known that if you do perturbation theory near upper critical dimension, which for this disordered model is 6 minus epsilon, and for usual model is 4 minus epsilon, then you do get the same critical exponents. Epsilon expansion is exactly the same. But if you go to the other extreme, if you jump from 6 minus epsilon to the interesting, physically interesting cases, for example, d equal 3 or d equal 4, then this conjecture is doesn't hold up to scrutiny. So, for example, in d equal 3 dimensions, it's known that the random field Ising model does have a continuous phase transition with non-trivial critical exponents by experiments and by numerical simulations. But we know that the one-dimensional Ising model doesn't even have a phase transition. So clearly something is not quite right. And if you go to 4D versus 2D, again, in both cases, we have a phase transition, but the critical exponents don't agree. So, well, so clearly then this is wrong, but then you go to 5 dimensions, then the same numerical simulations performed in 5 dimensions, they do give critical exponents which are the same as in 3 dimensions. And moreover, you can test the supersymmetric word identities in 5 dimensions by doing simulations, and you do find support for those. So in 5D we have SUSY, but when you go down to 3 and 4D, you lose SUSY.
Right, Slava, just to confirm, this is phase transition as a function of J at fixed disorder averaging protocol. That's right.
Well, you can study it either by sitting at a fixed disorder strength and varying the temperature, or you can study it by sitting at the fixed temperature and varying J, because there is a disordered fixed point, and you will flow to it from different points of the phase diagram. In fact, when you do numerical simulations, the nice thing to do is to sit at 0 temperature and just vary the disorder strength. This is the fastest way.
Okay, thank you.
So another interesting quirk is that there is a related story where instead of considering quartic Lagrangian, you consider cubic Lagrangian, which is known as the Lie-Yang universality class. So it's described by a non-unitary field theory in D-2 dimensions. And in that case, everything works out perfectly. So there is, numerical simulations. You can do numerical simulations in both cases again, and there is actually an interesting statistical physics connection with physics of branched polymers, and the critical exponents beautifully agree between branched polymers simulated in D dimensions and between the Lie-Yang CFT in D-2 dimensions. So there is always supersymmetry. So in our work, when we learned about this beautiful puzzle, we saw some possibility for us to do something. And so what we did so far is that we performed new checks. So the conjecture has 2 parts. So which of these 2 parts is the source of the trouble? So we started by checking the second part of the conjecture, the dimensional reduction. And we performed some new checks of this dimensional reduction using a different language from the one that was used before us in the literature, because people were usually studying these questions based on the Lagrangian description. But since we have this conformal field theory philosophy and the bootstrap philosophy, we wanted to see if there is anything suspicious with this dimensional reduction from the non-perturbative CFT point of view. And we didn't find anything suspicious. So it just beautifully, there's a consistent story, an interesting story that I'm going to talk about today. So this is something which is published. And the second part of the project is that, okay, a fortiori, if dimensional reduction is okay, it means that the first part of the conjecture must fail sometimes. And from the realization group point of view, a natural conjecture would be that this supersymmetric fixed point, it's so supersymmetry is an emergent symmetry at the fixed point. And for it to be an emergent symmetry, the SUSY break-in directions have to be irrelevant, which is the case near 6 dimensions. But then when you go sufficiently low, then some new relevant directions may appear in the realization group flow, and this renders the fixed point unstable. So this is a natural scenario which we are going to explore in this paper about to appear. Any questions at this point? Okay, so let's start then with the dimensional reduction story. But first, I would like to give you at least some kind of argument hand-waving argument of why you have the right to expect supersymmetry in this problem. It's totally non-rigorous, but it gives us some intuition about what may go on. So we studying field theory, we have to study this. As I said, we have to perform this path integral over phi with some fixed value of h. Normalize it and then average over h. So let us make an assumption that this path integral is somehow localizes to classical solutions, to classical configurations of the action S of phi h. So we keep h fixed, and we localize this path integral to classical phis, classical solutions of classical equations of motion. So this has something to do. This is actually not so wrong, because this has something to do with what I already mentioned, that this fixed point is believed to lie at 0 temperature. But now, okay, this is an unproven assumption. So then how can you implement it at the Lagrangian level? Well, you say that I do this path integral of phi, I insert a delta function, which localizes me to the classical solutions. But I want to count this classical solution with coefficient 1. And so this means that I have to normalize this delta function, multiplying it by the determinant of the operator, of the partial differential operator. So that's pretty natural. And then if you do this, then you can do the second step. You say, well, I'm going to introduce a Lagrange multiplier field omega to represent my delta function. And then I'm going to introduce two anti-commutative scalar fields psi and psi bar. These are Grassmann scalar fields to represent my determinant. So this becomes my new action. I got 3 more fields. But now I should not forget that I also have to integrate over h. And so let me perform a path integral over h, which is just a Gaussian path integral, so it's easy to be done. Now I get rid of h, and I get an action which depends on 4 fields, phi, omega, psi, and psi bar. And it is this action. And this action has supersymmetry. It has this particular Parisi-Sourlas supersymmetry. So the supermultiplet has fields phi, well, I wrote chi, has to be psi and psi bar and omega. And the dimensions of these fields are d over 2 minus 2, d over 2 minus 1, and d over 2. So in fact, this omega squared term has to be viewed as a part of the kinetic Lagrangian, so it fixes the dimension of omega. Then, okay, the dimension of phi is also fixed, and the dimension of psi and psi bar is diagonal. So from this form of the action, it's not clear that we have supersymmetry, but to see this, we introduce a superfield. We introduce a superspace in the superfield, and it's a very easy superspace because because the Grassmann directions, they are not spinors, they are scalars. So it's a non-unitary supersymmetry, which would not be allowed in empirical physics, but in statistical physics, it's totally okay. So our superspace has bosonic coordinates x and 2 Grassmann coordinates theta and theta bar. And the super rotations are just OSP rotations of this superspace. Very easy. And the superfield is just a linear combination phi of x, theta psi bar, theta bar psi, and theta theta bar omega. And in terms of these ingredients, the action just takes this very simple form. You take a super Laplacian, del squared plus 2 d theta bar, and the potential v of phi. So, and if you substitute, you expand in components, you end on the Parisi-Sourlas section. Very easy. So this Parisi-Sourlas supersymmetry, then it has the super rotation part OSP d/2. It has super translation part, which is just the R d/2. The supercharges are scalars and vectors, they're not spinors. And if we reach the fixed point and this supersymmetry has to be enhanced, we expect it to be enhanced to a larger supergroup, which is OSP d+1, 1/2. So this is going to be a super conformal field theory. So for this super conformal field theory, as I mentioned, there is this conjecture about the dimensional reduction. So what does it mean? It means that if we take the superspace R d/2 and if we pick on it some d-2 dimensional bosonic subspace, which is parameterized by this coordinate x hat, which is d-2 dimensional coordinate. So we set to 0 the fermionic directions and the 2 bosonic directions. This is a plane. Then the claim is that if you consider a correlation function of the superconformal field theory, we set all insertions into the plane, then this correlation function can be equivalently computed as the correlation function at the same positions of a non-supersymmetric d-2 dimensional theory with basically the same Lagrangian, but where you replace all derivatives by SUSY derivatives by normal derivatives, d phi squared plus v of phi. So that's this is the conjecture, and Parisi-Sourlas, they gave the proof of this in perturbation theory. So if you use super propagators on the left-hand side and Feynman propagators on the right-hand side, and if you use a little identity, which shows that when you integrate some radial function over all superspace components, then there is the 2 bosonic and the 2 fermionic components cancel each other. Then you can very easily prove that the perturbative expansion for these 2 theories just agrees. So after that, there were some non-perturbative arguments by Cardy and then later by Zaboronsky, which gave different proofs of this property, and which, you know, in particular Zaboronsky's argument, it has the flavor of the localization. It's kind of a localization type argument, but all of these arguments are based on Lagrangians.
Slava?
Yeah.
One question. This dimension reduction of an SCFT to CFT in d-2 dimensions, is this a general statement or supposed to be valid only in this type of Lagrangian?
So it was, before our work, it was argued based on these scalar Lagrangians. So we decided that that was precisely one of our motivations, is to see if this whole story could be reformulated as a pure CFT construction, and that's what we achieved. So we will see that there's going to be some reduction at the level of OPEs and at the level of CFT axioms.
I see. Okay.
So it's more general. It's not. It can be formulated generally.
Okay.
Any other questions? Okay, so this is the plan. So if you view it from the CFT perspective, then that's what we expect. We take a superconformal field theory in d dimensions. Its superconformal symmetry group contains the conformal group, in particular, of d-dimensional superconformal field theory. We set all operators into a particular d-2 dimensional plane, and we expect to find here a conformal field theory in d-2 dimensions. So whoever has been paying attention to the super conformal bootstrap in recent years will immediately say that this reminds very much the story of chiral algebra in n=2 super conformal field theories, which has been developed after this paper by Chris Beam, Madalena Lemos, Pedro Leando, Valgon Pilares, Leonardo Stille, and Balt van Rees. But even at a more even at a more elementary level, this story also reminds something which is known in conformal field theory literature as a trivial defect CFTs. So, and this comparison of how this story is similar and different from trivial defect CFTs is what I'm going to be paying attention now. So by the trivial defect CFT, we call this very trivial construction where you take some d-dimensional conformal field theory and we restrict all correlation functions of this theory to some d-prime dimensional subspace. So what's going to happen if we do this? Well, from the point of view of the subspace, the symmetry group of the d-dimensional theory is going to be broken to the d-prime dimensional conformal group, SO d prime plus 1, 1, and the ambient the ambient rotation SO d minus d prime. And so now we can take all the CFTD information and we can decompose it under this subgroup which preserves the defect. So what are we going to get if we do this? Well, of course, the information which was nicely packaged in d dimensions, it becomes a mess in d prime dimensions. For example, every CFTD primary is going to give rise under this reduction to infinitely many d prime dimensional primaries. And the reason why this will happen is that, first of all, if we have some d-dimensional primary and has a bunch of indices, then when we put it into the plane, then we can assign some of these indices parallel to the plane, others perpendicular to the plane. So it means that every representation will give rise to several representations, to several primaries when we do this. But there is also another reason, is that the primaries in d dimensions, they have descendants, they're derivatives. But if we take the derivatives perpendicular to the plane, then from the point of view of d prime dimensions, this will give rise to new d prime dimensional primaries. So this is going to be infinitely many primaries. And for example, this sort of reduction, okay, it's a very trivial reduction, but sometimes it's useful. For example, you may want to compute conformal block in a three-dimensional CFT, and you know that conformal blocks in three-dimensional CFTs are somewhat complicated. But for example, conformal blocks in two-dimensional CFTs, they have explicit expressions in terms of 2f1s, global conformal blocks. Well, using this reduction, for example, you can take a any three-dimensional conformal block and expand it as an infinite series of two-dimensional conformal blocks. Or in general, a d-dimensional conformal block is going to be an infinite series of d-prime dimensional conformal blocks. Infinite because there are infinitely many primaries in this multiplet, d-prime dimensional primaries. And for example, and these coefficients, they can be often worked out explicitly, and this has been done in a paper by Matthijs Hogervorst in 2016. So these formulas are even practically useful in some cases. But another feature of this construction, which is quite dramatic, is that this d prime dimensional theory is going to be non-local. So it's not going to have a local conserved stress tensor operator. This is physically pretty clear because, okay, this theory doesn't make sense by itself. It exchanges information with the bulk. And formally, it's also clear because we know the dimension of the stress tensor in d prime dimension has to be d prime, but we don't have such an operator in general in the d-dimensional CFT. We have an operator of dimension d, and that's not going to be conserved in d prime dimensions. So, so this is the trivial defect. And now, if we look at the comparable story for the Parisi-Sourlas dimensional reduction, we see that it's going to be different. It's going to involve the same kind of moving parts, but the outcome is going to be pretty different. What we will see is that one superconformal primary, superprimary, will reduce under this dimensional reduction to one, not infinitely many, but one d-2 dimensional primary. Well, up to some caveats that I'm going to mention. Sometimes it's going to be 0 and not 1. And so the second feature of this construction is going to be that the superconformal block in d dimensions is going to be precisely equal to the d-2 dimensional conformal block. Not some infinite sum of conformal blocks, but just like 1-to-1 equal. And finally, this reduced conformal filter in d-2 dimension is going to be local. So it's going to have a conserved stress tensor operator, unlike in this trivial defect. So all of these features, people, they could have been suspected from these Lagrangian arguments, but we will show that they basically follow from CFT axioms, superconformal field theory axioms. It's actually pretty easy if you take the right perspective to see all of these properties. For example, let's look at what happens for superprimaries in d dimensions first, before we do dimensional reduction. So the superprimaries in d dimensions, they are defined as the primaries in d dimensions. By the condition that the special superconformal generators Ka, where A is the index which can take either bosonic or fermionic values. So this commutator should vanish. And the first thing, for example, you can discuss is how this superconformal primary, how does it decompose under conformal group in d dimensions, not in d-2, but in d dimensions. So the way you do it, you take the multiplet, you decompose it, you expand it in theta, theta bar. So now you have 4 fields, or 1, or 2, or 3, or 4, and they have dimension delta, delta plus 1, delta plus 2. But these indices A, they are OSPD/2 indices. So if you want to decompose under the d-dimensional conformal group, we should set some of these indices to theta, theta bar. And this way, we are going to get CFTD primaries. And since we can do it in several ways, first by expanding in theta, theta bar, as I did here, and then setting these indices also to theta, theta bar, we will end up with several conformal primaries and one superconformal multiplet. And so if, for example, you start with the graded traceless symmetric primary of spin L, this OA, then by doing this construction, you will end up with 5 bosonic CFTD primaries and also some fermionic primaries. Because Slava? You can, yeah.
So one question, just to make a connection with this representation theory of superconformal algebras, the usual ones that one knows. I don't quite see, how is it that these indices also take values? I mean, these indices also can be theta, theta bar, because usually I think of superconformal primaries being given by just the is labeled by the conformal primary that is killed by SS, the superconformal, the conformal supercharges. So I just want to make connection with the representation theory that is more familiar, perhaps.
So you're asking why is this the right condition to impose on?
No. I'm just talking about this index that could, as you said, take values also to be theta bar.
Ka. So the point is that normally in so the structure of this super group is different from the ones that we have to do in we deal with in high energy physics. So here we really have special conformal generators, and then we have the special super conformal generators, but they have this k theta. So k theta and k theta bar.
So is it that the k theta is conformal supercharges, or I shouldn't think of it like that?
You can, yeah, you should think of them like that. Yeah, k theta conformal supercharges.
Okay, thank you.
But the point is that unlike in the usual supergroups, the commutation relations. I mean, if the usual supergroup you call those conformal supercharges by k, you don't gain anything because I mean they're clearly different objects. But here, if you call them k theta, then the commutation relations they just are written extremely easily using the metric of this OSP d/2 superspace. So it's really like, I mean, you just take the usual formulas for the conformal group that you're all familiar with, and you just allow the index A to run not from 1 to D, but to 1 to D plus theta bar. And you get, you replace the usual metric by the super space metric, and you get the commutation relations of the super algebra.
Okay.
It's as simple as that.
So, and the spins of the supersymmetries, are they zero? What are the supercharges?
I missed the beginning of the question. Sorry.
What are the spins of your supercharges?
So the spins k theta and k theta bar are scalars under the rotation, and k mu are vectors, of course.
Right. So the supersymmetries are scalars under rotation.
Yeah.
Okay. Thank you.
But there are also some rotation. For example, there are some super rotation generators which are m mu theta. Those are vectors.
But there are no spinners under rotation.
There are no spinners whatsoever.
Thank you.
So these 5 bosonic primaries, keep this in mind. This is going to come back in a second. And so so now I would like to formulate some rule for the general dimensional reduction. So because the rules that we have in the literature, they were formulated for correlation functions of the fundamental field, basically phi. But now if we are doing the general CFT problem, then we have to tell how to reduce any correlation function of any primary of our d-dimensional SCFT. So so we have to think a little bit, for example, you should think like, okay, that the rule that you would like to come up with, it has to be, of course, consistent with the OPE in d-2 dimensions. For the way the rule can be consistent with the OP is that if there is some symmetry structure. And so the symmetry structure that we are going to impose on our dimensional reduction is that we will not keep, so dimensional reduction consists to set the fields into the plane. That's the first step. But also we will only keep the states which are invariant with respect to OSP 2/2 subgroup, which leaves this plane invariant. So this rotation subgroup around the plane. So we will only keep the states which are singlets under this subgroup. So this is the way, this kind of a truncation of the theory and which ensures that this reduction procedure is going to be consistent with the OPE, will lead to the closed OPE. Of course, if you are dealing with scalars, then this is automatically satisfied, but we claim that this is the natural extension of the rule to the full SCFT. So let us see what are the features. So when I want to get this OSP2/2 invariant state, there are two ways to get it from an operator in SCFT. So the most general SCFT operator, it's a descendant of some superprimary. So it's so this is a superprimary OA1AL, and now I take a certain number of super derivatives, and I put everything into the plane. So there are two ways to get a state which is a OSP2/2 invariant. Either I can take each one of these indices A or B, I can take it along the plane. Of course, it's going to be invariant. But there's another way. I can take a bunch of these indices and I can contract them with the metric invariant under these OSP2/2 rotations. So it's the metric of this G2/2 I denoted. These are the two ways. And so I'm going to split all the singlets, states. I will split them into S0 plus S1, and I'll call S0 the space of singlets which do not involve G2/2. And I will call S1 those ones whose construction needs at least one G2/2. So these are both singlets, but I will now show that in fact you should think of this S0 states as the one which survive in D-2 dimensions, but these S1 states, they will decouple in some sense. But as a first step, we just define the D-2 dimensional CFT to consist of all singlet operators. So this is nice because this definition is automatically closed under OPE. So if I take two operators which live on the plane, I collide them in the OPE. These are two SCFT operators. If they're both singlets, then all operators in the OPE are also singlets. And so my OPE is automatically closed and I get a good OPE algebra in D-2 dimensions. That's nice. And now comes the second observation that S1 operators, those ones which involve this G2/2 metric, they decouple from any singlet, be that S0 or S1, on this plane MD-2. So such correlation functions where I have S1, at least one S1, and several S0s or S1s, such a correlation function on the plane is guaranteed to vanish as a property of a superconformal field theory. And the proof of this fact is very easy. You kind of, if you think about this a little bit, you notice that this correlation function, it will necessarily involve at least one super trace of this metric G2/2. And since the super trace is zero, it means that it's going to vanish. So it is this property, which is the crucial difference of this story from the trivial defect story. Because we could also do, for trivial defects, we could also only keep the singlets, but this would still give us an infinitely many primaries in D-2 dimensions. But because of this property, basically, out of these infinitely many primaries, only one is going to survive. So this is the claim. So if I take a superprimary and if I do this dimensional reduction, and if I keep only the zero part, which means that I have to keep here only the indices along the plane, and here I only take derivatives along the plane. This means that all these states are the D-2 dimensional descendants of this particular operator, which is a primary of the D-2 dimensional theory. So I can package all of these states into one conformal multiplet. So every SCFT superprimary, it gives rise to just one CFT D minus 2 primary and not infinitely many. So this is almost trivial, but okay, there is one interesting complication, interesting subtlety, is that some superprimaries, they actually will descend to 0 under this reduction. And this you may have suspected because, you know, the representations, they are parameterized by the Young tableau, and there are more Young tableau in D dimensions, and there are even more Young tableau for OSP than for SO D minus 2. And so those Young tableau which do not have their counterparts in D minus 2 dimensions, they project to 0. So this has, I mean, this is a complication. So this basically means that this reduction, it only goes one way. So we can, you know, there are certain quantities. So if you know the SCFT, then you can construct everything you need to know about the CFT in D minus 2 dimensions. But perhaps you would like to go the other way around. Like, okay, suppose that I already solved the 3-dimensional Ising model, and I would like to know what is this superconformal field theory in 5 dimensions. Can I reconstruct everything easily or not quite? Well, it turns out that some of this information is lost. You have to reconstruct it, you have to solve some sort of bootstrap problem. It's not automatic. So I also, well, there is also some story for the stress tensor. You can show how it arises from the superstress tensor, but maybe I'll skip it in the interest of time. And if there's questions, I'll come back to this later. So let me show you some concrete results. It's of this picture.
Sorry, one question.
Yeah.
So you briefly mentioned a possible relation to the chiral algebra story. So is there any? I mean, this condition of imposing singlet condition under OSP 2,2/2, is it kind of like the twist that they do?
I mean, there are at the moral level, there are multiple similarities because, for example, this the fact that the reduction works only for singlets, and they also have some subsector of the theory which they keep these Schur operators that they keep in the reduction. The reduction has a homological flavor, as you see. There are this S0 plus S1, and S1 projects to nothing. So the story also has some homological component. Well, that's interesting, but I think their story is much more complicated. So our story, as you see, is you don't have to know much about superconformal field theory, and I definitely knew next to nothing about superconformal field theory before I started working on this project. But in there, I mean, their story is much more non-trivial.
Perhaps a related question is there any particular aspect of this supergroup that you crucially use?
Well, I guess there is one. So the aspect of the supergroup is that, well, there is this property that there is this OSP 2/2 subgroup whose which has only one invariant tensor of supertrace 0.
Okay.
This is the crucial property.
Okay.
So if other supergroups have this property, then basically the same mechanism will work.
Okay, thank you.
So to finish this first part of the talk, and then I'll have a few minutes to say something about the second part, is that I want to show you the consequence of this relation that the superconformal block in D dimensions is equal to the conformal block in D minus 2 dimensions. So first of all, you have to show this property, but it basically follows from the Casimir equations. So both of the left-hand side and the right-hand side, they satisfy the Casimir partial differential equation. And the structure of this equation is very similar because, as I said, the commutation relations of this superconformal algebra are basically obtained by commutation relations of conformal algebra replacing the metric of RD by RD/2. So this is true. We proved this. But now notice that something interesting follows from this equation. So we know that in any superconformal field theory, we can decompose the superconformal block in d dimensions as a sum of usual conformal blocks in d dimensions. So we look at the superconformal multiplet, we decompose it into conformal multiplets, and there are always some coefficients, relative coefficients that you have to fix. And as I showed, for example, if you look at the symmetric traceless superprimaries, then they decompose into five bosonic primaries in d dimensions. So I know that the left-hand side is a sum of five conformal blocks in d dimensions. And so I get this corollary that, so the left-hand side is a sum of five blocks in d dimensions, and the right-hand side is one block in d-2 dimensions. So there should be some coefficients which express one block in d-2 dimensions as a sum of five blocks in d dimensions with known deltas and L's. So this is just like, at face value, this looks very unusual. So if somebody told me beforehand that a relation like that should be true for conformal blocks, I would have been surprised. In fact, people have known many recursion relations for conformal blocks, but nobody has worked out this conformal relation before. And the reason why is that the order of dimensions is different. Like normally people take a block in d dimensions and then decompose it in terms of small number of dimensions, and this leads to infinite sums, as I explained. But here we have a finite sum. If you read from left to right, then you get a finite sum. So in fact, the claim is that this recursion relation is true, and in fact, we found it, and we found these coefficients with the benefit of this argument. And this recursion relation inverts this infinite series that we found by Hogervorst. So this is cute. I personally found it pretty cute, and it's kind of concrete and not something which could not have been guessed if you didn't know about this Parisi-Sourlas supersymmetry. So that's basically finishes the first part of my talk, and if there is a little bit of time, I would like to mention something about the second part of the talk, but I would probably need 5 to 10 minutes.
Yeah, sure.
Something meaningful.
Yeah, sure. Please do go ahead.
Okay, thank you. So this is something that I already said, that the natural way to resolve the puzzle is to find some RG direction which makes the supersymmetric fixed point unstable. And I mean, this is a very natural. Point of view, and so you may have asked, okay, why haven't this been solved many years ago? Well, because there are some subtleties. There are some subtleties in how you perform RG in this disordered field theory. So let me explain. So if you do like what everyone does with this disordered field theory, if you want to use RG, you use the replica method. Well, that's most people are familiar with this, but so when you do this replica method, you replace your field theory with the Lagrangian d phi squared plus v of phi. You have n times replicated Lagrangian, and then once you integrate out the magnetic field, you end up with this term which couples all replicas together, which has this form phi 1 plus phi n squared minus h over 2. So this is pretty standard, and now you have to take the limit n goes to 0 in this Lagrangian, and you have to look for fixed points, and you have to study the anomalous dimensions and so on and so forth. So this is pretty standard, but now let us look at this Lagrangian. There is something weird about it. The thing is that we like doing a renormalization group when there is the Gaussian fixed point, and then we perturb this Gaussian fixed point. There is some marginal perturbation in the upper critical dimension, and it becomes weakly relevant. Then you do perturbation theory. So this is something that we, for example, what happens for Wilson-Fisher, and that's something that we know and love. But here, that's not what you see. So in fact, as I told you, this upper critical dimension of this theory is 6D. And if you just stare at this Lagrangian, there is no interaction here, which is marginal in 6 dimensions, because what you have here is that there is some quartic term in the V of phi, which is irrelevant in 6 dimension, and then there is this quadratic term phi 1 plus phi n squared, which is relevant in 6 dimension, and this marginal coupling, it comes out somehow as a product of the relevant coupling which flows to infinity, this h, and the irrelevant coupling which flows to 0. Or at least that's what people say. And that's like when I first looked at this, I said, no, there's something which is not what I would like to be doing. And another way to see it is that if you look at the propagator, which you compute from this theory, just from the Gaussian part of this theory, you see that the propagator has 2 parts. There's like one part which is 1 over k squared, and there's another part which is 1 over k to the 4th. So it doesn't have the good scaling, the propagator. It's like, it looks like it mixes, what basically it smells of is that you didn't separate carefully the fields of the right scaling dimensions. So you are doing perturbation theory, that's what most people are doing. They start doing, take this Lagrangian, they do perturbation theory, but they don't have the basis of good scale, of fields of good scaling dimension. And of course, if you do perturbation theory without having this basis, you are lost. It's very hard to do this. So that's basically why this problem of what is the direction which destabilizes the RG flow is still unsolved. But in fact, if you look at the literature, there is a nice and very poorly known paper by Cardi from 1985, which does exactly what we need. This paper has like, I don't know, 20 citations, and it has not been used at all for this purpose. And our hope to say something new in this old problem is precisely because we are the first people who take this Cardi formalism seriously, probably even more seriously than Cardi himself, and try to use RG using this formalism. So what Cardi proposed was that he said, okay, I'm going to take a field transformation from these fields phi I, which are the replicated fields, to these fields phi, curly phi, omega, and chi I, which satisfy this linear constraint, the sum of chi I equal to 0. And it's okay, it's some field transformation that Cardi cooked up. Okay, there are various ways to motivate it. But the interesting thing about this formalism is that it breaks SN invariance. So usually when you do this replica, or rather it does not break SN invariance, but it renders SN invariance non-manifest. So in the replicated theories, SN invariance, which performs permutes and replicas, is of course very important. So people were very reluctant to sacrifice it. But what basically Cardi says is that, okay, if you want to have, either you render it non-manifest, and then you have a nice RG formalism, or if you keep it, but then your RG is a mess. So we say, okay, that's fine. We will live with the non-manifest Tyson invariant, but at least we will have a nice RG. So once you do this Cardi transform, you end up with the Lagrangian, which has several pieces, L0, L1 plus L2. And the nice thing about L0 is that it basically is precisely the supersymmetric Lagrangian. So I gave you at the very beginning of my talk this hand-waving way to arrive at the SUSY Lagrangian, when I said, let's just keep classical solutions of the equations of motion. The bad part of that derivation was that it was basically impossible to check it for self-consistency. Okay, take it or leave it. On the contrary, this Cardi derivation, it contains the keys of checking its all self-consistency, because there is L0 part of the Lagrangian, which is precisely what you want. It's the SUSY Lagrangian. But there are also these correction parts, L1 plus L2. And if you don't drop these correction parts, then you didn't make any error. So the problem is then to understand, okay, under which conditions are you allowed to drop them and when not. And so since we have this SUSY Lagrangian, it means that now we do see the upper critical dimension 6, because there is the fields phi, omega, and chi, they acquire the scaling dimensions such that the interactions chi squared v double prime and omega v prime, they are precisely marginal in 6D. And what about these correction terms L1 and L2? Well, L1 term is pretty easy. It contains all terms that vanish in the limit n goes to 0. So, which basically means that you can drop them. And L2 term, L2 part of the Lagrangian, it contains all terms which are irrelevant close to the upper critical dimension. So there's a whole bunch of them. I mean, in fact, infinitely many of them. Okay, they have various complicated form like phi chi cube, chi to the fourth, and whatnot. And if you drop these terms, then you end up with a supersymmetric fixed point. But now what you are supposed to do is that you are supposed to see if some of these terms actually become relevant. You have to compute anomalous dimensions of these terms, and you have to see if some of them become relevant at some critical dimension below than 6. Well, even this seems like a very simple thing to do. So why are you working on this for 2 years already? Well, because even though this, we immediately recognize that this is a very nice starting point for the project, we had to overcome a lot of conceptual difficulties along the way. And in fact, this is probably the most complicated renormalization group system I ever looked at in my work. So what are the complications? So first of all, there are all of these terms. You have to understand which of them break supersymmetry, which of them don't break supersymmetry. Not all of them break supersymmetry. So, yep.
So just to be clear, this chi-i's are Grassmann odd or Grassmann even?
So no, chi-i's are not Grassmann. Thanks for asking. So chi-i's are just linear combinations of phi, so they are scalar fields, but there are -2 scalar fields. And so in the limit n going to 0, you can, since they enter into this L0 Lagrangian only at the quadratic level, you can replace in this L0 Lagrangian chi I squared by psi bar and d chi I squared by d psi bar. And this will give rise to exactly the same randomization group flow.
So the statement is that if you analytically continue in n and then you take n going to 0,
Yeah.
answer at least just with L0 is same as, you know, like replacing chi I by Grassmann fields. Is that
Yes.
this?
Yes. Yes. That's this is the claim. So this can be justified at various levels, and we think this is not the most problematic part of the story. But notice that in this L2 term, in the L2 Lagrangian, there are some fields which involve different parts of chi, for example, chi cube, chi to the fourth, and so on. So these fields, they cannot be written in any way in terms of psi and psi bars. So when we do randomization group, we actually have to work in the basis of the chi's. So we notice that if we only have L0, then this is equivalent to SUSY. But in order to study the randomization group flow and the directions which are relevant, which are irrelevant, you cannot go to this psi bar basis. You have to work in the chi basis, which is another complication. So that's what I say here. So some of the operators which we are interested in, they cannot even be written in terms of SUSY fields. So they are not captured. The anomalous dimension is not captured by the supersymmetric field theory. And finally, this complication is that we are not interested in relevant, in whatever operator which is relevant. We are interested only in those operators which are relevant, which have a SN invariance. Because the microscopic theory had a SN invariance, the replicated theory. And once we go to the Cardi basis, this SN invariance is no longer manifest, but it is still there, and we should only look at the perturbations of the RG flow which somehow originate from SN singlets. And it turns out that not every operator in this list is an SN singlet. For example, phi chi cube turns out to be is not a singlet, so if you just look at this operator, say, oh, well, this operator looks like it has a small anomalous dimension, maybe that's the one which becomes relevant. Well, that's going to be wrong, because this operator by itself is not, it will never be generated in this RG flow. So, so there's a whole bunch of complications that we resolved more or less to some degree of satisfaction. And we have our scenario, which we are going to advance in our paper, is that we identified several random field Ising model operators which have these properties that they are singlets, that they break supersymmetry, and that they become relevant at sufficiently low D. And the operator which becomes relevant at first is this operator that has the form omega chi cube, omega sum of chi I cube. So we computed its anomalous dimension at a two-loop order in 6 minus epsilon, and if you just plug in blindly, if you extrapolate this formula, then you get that it becomes relevant for D around 4.1 dimensions. And if we do the same story for the branched polymers, for the Lie-Yang universality cluster, we don't find any relevant SN singlet operator, applying exactly the same set of rules. So, well, that's basically the story. Okay, there are some consequences for the latest Monte Carlo simulation that people may use perhaps to check our scenario, but I think when we are done with our project, the main value is going to be that we will set up this conceptual framework which will allow to perform very detailed tests of this RG flow from various directions. So hopefully our work is going to, it will lay down some foundations for this study. And okay, probably we have all the ingredients. We identified all the important ingredients. Okay, we performed a bunch of computations, but some of these computations can be pushed to higher loop order and whatnot and so on. But so I think now I'm hopeful that with our work and with in a couple more years, we will have a much clearer picture of this puzzle. So thanks for your attention. Sorry for taking for going over time. I'm done.
Thank you very much. Let's unmute and clap. Questions?
Slava,
I'm sorry, Shiraz, I missed your question.
yes, I'm sorry. Could you? I just wanted to get to the superconformal algebra that arises in this Parisi-Sourlas story. I wanted to understand that a little better, please. So could you tell me what is the bosonic part of the superconformal algebra, please?
It's the bosonic part is okay. Maybe I can fulfill my promise and write some equations. So for this, well, okay, I can say this. It's the conformal algebra, so times SP2.
Times SP2, and the odd generators are vectors under both SO d,2 and SP2. They transform the bifundamental bivector.
Exactly. They bifundamentals.
Okay, thank you. Sorry, maybe one other question. You know, in the usual story, superconformal algebras have short representations, which then lead to protected operators. Is there an analog of that with this superconformal algebra?
Yes, there is an analog. So, for example, the super stress tensor lies in the in the short representation of this superconformal algebra, because it's super conserved. So there are these short representations. So you can say you can use this condition to extract the dimension of the super stress tensor, and it comes out to be equal to d-2. So in fact, inside the super stress tensor, the lowest component of the super stress tensor becomes the usual stress tensor in d-2 dimensions, but the highest component of the super stress tensor, which has dimension d-2 plus 2, so d, it becomes the stress tensor in d dimensions.
And apart from the stress tensor, are there other interesting short multiplets that play any role in your analysis? Something like the chiral primaries of.
No, we have not identified anything like chiral primaries. We have not identified any isolated representations. So it looks like all unitarity bounds are. I mean, there are no unitarity bounds because this algebra is not unitary. But it looks like there are also some conservation type conditions and nothing particularly deep.
Thank you.
But from a d-2, so non-supersymmetric point, from the d-2 dimensional non-supersymmetric point of view, you don't expect any. You don't expect any. Either you don't expect any other short operators, or you expect, if they are present, to give rise to vanish in this dimensional reduction. Is that correct?
Are you asking if I expect that this d-dimensional SCFT should contain any more short representations except for the stress tensor?
Yeah.
No, I would not expect that.
I see.
Yeah.
I see.
There's some weird, there's some interesting, so in fact, there are, perhaps I should say, because in fact, in our second paper, so we did this first paper on the representation theory, basically. And in our second paper, actually, some parts of this story, they became very useful because, so I gave you this this property here that when we take a superprimary in d dimensions, then when we project to d minus 2 dimensions, then we are supposed to keep this as 0 component, right?
Mm.
But what about the other components? Do they have any meaning? I mean, any interest and so on? So it turns out that the other components of the superprimary, for example, if you set these indices to theta and theta bar, so these are precisely the operators. These form a certain class of perturbations of this supersymmetric theory, which can be produced by SN invariant perturbations of the replicated theory. And this means, for example, that if we know the dimension, since people have computed many things about Wilson-Fisher theory, and we kind of, in first approximation, we know a lot about the dimensions of the operators downstairs, we can predict dimensions of operators upstairs of those operators whose dimension we would like to know in order to say if the supersymmetric RG flow is stable or not. Or at least some of these operators. We can say something about their dimension. So there is an interesting, yeah, so it looks like both parts of the supermultiplet, they have some physical meaning. So if you set components to theta, theta bar, it's an interesting perturbation in d dimensions. But if you set components to mu in nu, then you get an interesting d minus 2 dimensional operator.
By the way, Slava, I have one comment. Perhaps this could be relevant towards looking at these short representations. So if one could compute superconformal index of this theory and project onto OSP2, OSP2/2 singlets, and that should capture all the short representations that you expect to have analogs in d minus 2 dimensions. And if that set only consists of stress tensor, that is, you know, then that would be just a direct confirmation of that, right?
But well, this sounds interesting. But how would I compute the superconformal index of this?
Well, I would expect using the weakly coupled description of the theory.
Okay.
Yeah, just one look. Yeah.
Yeah. So this yeah, this is kind of an interesting. We can generalize your comment to the following fact. So usually we say, okay, the Ising, okay, the Wilson-Fisher flow, okay, people have been studying it for a long time. We know a lot of things about it. Now it turns out that we can, with the Wilson-Fisher flow in 4 minus epsilon dimensions, we have this supersymmetric flow in 6 minus epsilon dimensions associated. At least in perturbation theory, they agree. So in our work, we use it mostly, we use this correspondence, but only in one direction. We say, okay, since we know a lot about 4 minus epsilon, we can learn something about 6 minus epsilon. But you could also turn this around and say, okay, the fact that this SUSY flow exists, does it allow us, can this allow us to learn something more about the Wilson-Fisher theory? And I am not aware of any useful work in this direction. So it's kind of fascinating it would be fascinating if this supersymmetry could help us learn something about the Wilson-Fisher.
And also the upshot of the story was that in d equals 5 there is a super analog of the Ising model also, right?
So this supersymmetric field, super analog of the Ising model, it exists in any D.
Right.
in some D it's unstable, meaning that it exists, but you do not reach, the RG flow does not flow to this fixed point, that it flows somewhere else. And in 5D, not only it exists, but it's also stable. So this renormalization group flow, that the disordered renormalization group flow, it flows to this fixed point and not somewhere else.
Yeah.
So in fact, that's something that the fact that it exists. So I said that this supersymmetric field theory exists in any D. These supersymmetric fixed points exist in any D. So this is an assumption that, you know, after many checks that people performed and we also performed, okay, in our second paper, we cannot get crazy, we take this for granted. But, you know, it would be, maybe there is some room for further work, even to clarify, you know, to clarify one aspect of the story that I am not sufficiently knowledgeable to say something authoritative about. So in some old literature, like in the 70s and early 80s, people mumbled some words about the possibility of spontaneous SUSY breaking of this Parisi-Sourlas SUSY. But I have a feeling that that it was not very well done. You know, people read some papers of Wheaton which were coming out at the time, and they said, "Oh well, maybe also here some SUSY can be spontaneously broken and so on." So, okay, you know, my knowledge of SUSY is not sufficiently to like quickly see if the spontaneous SUSY breaking can happen for Parisi-Sourlas or not. We believe that it doesn't happen, or we take this assumption it doesn't happen. But if there would be some way to clarify this and to ascertain this a bit better, that would be very useful. Yeah.
So, hello.
Yeah.
So usually this spontaneous symmetry breaking, so, you know, is said in the context of some systems which are not ergodic, which are glassy or something. I think that's what people usually say, that somehow you can characterize glassy behavior by trying to see whether there is a breaking of Parisi-Sourlas. And then correspondingly on the replica side, by breaking off from replica symmetry or something. But so you know, like, I'm just trying to understand, you know, like what you're saying. So
no, in fact, there are two parts of papers which mention spontaneous SUSY breaking. There's one part of papers which I think they just don't know what they're talking about. So they talk about spontaneous SUSY breaking even in a situation where the RG flow doesn't have initial supersymmetric RG conditions. So there's no supersymmetry is explicitly broken. And I mean, there's just, I mean, one shouldn't be talking about SUSY in the first place. There's no spontaneous SUSY breaking period. And I think this is what happens for the glassy behavior. So I think whoever talks about spontaneous SUSY breaking for glassy behavior in this theory, I think is just misguided. But then there are some papers, in particular the paper of Parisi-Sourlas, which say, okay, even if we have exactly SUSY initial conditions for the RG flow, it still may happen that SUSY is going to be spontaneously broken in the infrared. So this is a reasonable question. And I don't know if if this can be answered. So, for example, we assume that, okay, of course, if the theory flows to a fixed point, and we don't expect there's going to be SUSY breaking because it's just a SCFT, and we don't expect necessarily a flat direction in this case. But suppose that we take suppose we take an RG flow with exactly SUSY initial conditions in the UV, and just some negative mass squared, so that we expect that the Z2 invariance, for example, is going to be spontaneously broken in the infrared. do we expect that SUSY will also be spontaneously broken, or do we expect it's going to be preserved? I would say it should be preserved, but I cannot give a rigorous argument.
I mean, just a statement. I mean, even if there is an explicit breaking, you can still talk about spontaneous breaking, right? Like this is what we do with chiral symmetry. This is what we do with chiral symmetry in QCD. That is, there are explicit relevant operators which make break chiral symmetry in the QCD.
Because the chiral symmetry is broken extremely weakly.
Yeah, I mean,
but I don't think here supersymmetry is going to. Here supersymmetry in the UV is broken at order 1.
Yeah, so that's a question, whether if it is broken softly in some sense, you know, like then it might still be, you know, if the endpoint is nearby somewhere to somewhere, you know, like where there's supersymmetry, then it makes
if this could be somehow argued, then I agree, but I have a feeling that many people in that community, they don't have this picture as clear as you're saying this now. I agree with what you are saying, but I have a feeling that many people don't.
Can I ask another question? So is there a way to change your theory in certain way that, you know, like you turn off these relevant deformations? Like, do you know how to fine tune it so that you do get the, you know, the critical exponents expected?
Yeah, so we that's what I was saying on my last page. So if this operator becomes relevant at which we identify, if this is the worrisome operator, if indeed this scenario is true, we can identify in the UV an operator to which gives rise to this perturbation in the IR, and we can try to see if the coefficient, if this operator in the UV can be fine-tuned to kill this perturbation. And one natural tuning that you can perform, you can tune the disorder distribution. So, for example, you can take, instead of taking the Gaussian disorder distribution, you can take some distribution which has a non-trivial kurtosis and so on. And by playing with this distribution, perhaps you can. We believe that you could kill this perturbation, and then people on the lattice who do simulations on the lattice, they could see this, because on the lattice you can take different distributions, and in fact, in some cases, people did perform checks with different distributions. For example, in D=3, but in D=4, no. So there's not so many. These are complicated numerical simulations, and there are not so many of them available, and hopefully if our scenario is right, and it could be, I mean, in the best of the possible worlds, that could be actually relatively easily confirmed. But because there are some other scenarios which say that this supersymmetric fixed point just doesn't exist in say in 4D, that because it just goes into some complex plane, whatever, it just disappears. So there are such, on the market in the statistical physics literature, there are such scenarios. And of course, if it doesn't exist, then you can tune whatever you want, but you will never reach it. But we say no, the SUSY fixed point exists in any D above 3. So, okay, if it exists, you can fine tune to it.
Okay, thanks.
Slava, one more question. This nice relation between the blocks that you found between the blocks in D dimension and blocks in D-2 dimensions. Is there a way to understand this relation bypassing the supersymmetry?
Well, once we derived, so the way we derived this relation, no, to understand, no, I'm not aware of any understanding, but there is a way to derive this relation
by inverting this.
So in fact, the way we derive this relation is this. Okay, we Using supersymmetry, we guess that there has to be a relation of this form with 5 couplings, with 5 coefficients. Then by using recursion relations for conformal blocks, we fix these coefficients because it's enough to expand. So each of these conformal blocks is an infinite power series, but just by expanding, by keeping the first few terms, you can already unambiguously fix these coefficients. Then you check that it works for the first 100 terms, so happy. But then we told about this, then there's a third way to prove this recursion relation, namely to ask Hugh Osborne. So when we asked Hugh Osborne, then he took out his arsenal of all sorts of recursion relations that he considered in his papers, and he found a particular magic linear combination of all those recursion relations which produces this relation. So he obtained a proof of this recursion relation by this, but only after we told him that it exists. So it would be difficult to guess it, but if somebody tells you, then you can prove it.
I see. Okay. And this basically comes from the connection between the. Here also, are you using the fact that this G11, this thing is super traceless?
But in a sense, yes, because this relation between superconformal block and conformal block in d-2 dimensions, it kind of, the fact that only one conformal block appears on the right hand side,
Right,
it's a feature of this dimensional reduction, which is a consequence of super tracelessness. So I'd say morally, yes, I'm using this.
I see. Okay, thank you.
May I ask a question?
Sure.
So this is,
Hi, Gautam.
hi, this is, yeah, hi. So this is about whether there is a possible holographic context in which your dimensional reduction can be understood instead of, in terms of bulk geometry.
I haven't thought about this at all. It's I gave this talk already several times, but it's the first time I'm asked about the holographic connection. I guess somebody had to ask sooner or later, but I have not prepared a good answer. No, I really have no idea. I guess I mean, holography has been so rich to accommodate basically any phenomenon of theoretical physics. So I would be surprised if it couldn't accommodate also this, but I
mean, it seems that it cries out for some geometric understanding, the kind of dimensional reduction that you were doing. Maybe in terms of, I mean, you were talking about defects initially. I mean, it could be some 4-dimensional true, sort of brains or something, and yeah. I'm not sure. Of course, you did mention that in terms of defects, it would be non-local. So yeah, it's probably not some. It's probably not some other brains. Yeah, I don't know, but it would probably be interesting to think of some brain intersection or something, and near horizon geometry of this, which breaks supersymmetry and also automatically sort of incorporates the dimensional reduction that you have. I mean, it's lovely stuff that you're doing, but some more geometric understanding would probably be good.
All I can say is that so there is one sign that kinematically it's consistent with ADS, because Well, I'm not sure if it's a big evidence or small evidence, but Xinan Zhu, so after he knew about this recursion relation for conformal blocks, he derived a similar recursion relation between Witten diagrams in d minus 2 dimensions and d dimensions, which I guess could be seen as a sign that kinematically at least nothing goes wrong if you try to put this story in ADS. But okay. But on the other hand, Witten diagrams can be expressed as sums of conformal blocks, so maybe it's not so surprising. So I don't know. I'm not very much an ADS person. I find it fascinating personally that perhaps I can mention another connection that I find personally like something that I would like to understand better in this context is that there is another instance where supersymmetry occurs in statistical physics. Okay, we have an appendix about this in our first paper. Is this in the problem of critical dynamics? So when we take a conformal field theory at equilibrium, and now we start like driving it, coupling it to some time-dependent, measuring some like time-dependent correlation functions and so on, then this gives us some theory in d+1 dimensions. But now this theory, so this you can do with any CFT, like with the Ising model, for example, but this theory in d+1 dimensions, if you do it this way, it doesn't have any interesting d+1 dimensional symmetry. So the symmetry really remains the d-dimensional CFT and the dilatations against time direction. But there is actually, on top of this, there is a supersymmetry, because you can view the fluctuation dissipation theorem for this time-dependent critical phenomena as a word identity, as a supersymmetric word identity for supersymmetry. And so this is something that is relatively well known. Okay, it's in Zinjusten and so on. But what I find fascinating is that okay, we have a good handle on d-dimensional CFTs. Okay, in some cases we can solve them exactly as in 2D. In other cases we have maybe bootstrap handle on them on 3D and so on. But we have very little handle on this dynamical critical phenomena in 2+1 or in 3+1. So these people, like basically what I find really disturbing is that, okay, let's take two-dimensional Ising model. Okay, it's exactly solved. You would think that you could somehow use this exact solution in 2 dimensions to learn something about 2+1 dimensional critical dynamics for the Ising model. Because this becomes a sort of bootstrap problem. So I have to find a 2+1 dimensional supersymmetric theory, and it's going to be again some sort of Parisi-Sourlas type supersymmetry, which reduces under dimensional reduction now. So now dimensional reduction is from 2+1 to 2 to the Ising model that you know exactly. So can we find such a 2+1 dimensional theory which reduces to 2-dimensional theory that we know? So this is a bootstrap problem of critical dynamics, but that's not the way critical dynamics is approached in the literature. In the literature, it's like, okay, you solved 2-dimensional theory, great, but now I'm just going to start from scratch. I'm just going to write again the new perturbative expansion, and I'm going to, like, I have to redo everything. So this is looks like very inefficient, and hopefully this Parisi-Sourlas. So there the Parisi-Sourlas supersymmetry always works, so there is no problem with RG stability or anything, but so I think I think this move to Parisi-Sourlas supersymmetry, and it will be nice to look carefully at all of its instances and maybe try to do something from this algebraic bootstrap perspective.
Right. Thank you.
Hello. So
Hello?
I just wanted to, like make a comment regarding this Gautam's question. So I guess one way to think about it is that, like you should have some kind of a Parisi-Sourlas supergravity on ADS. And, like some supergravity in ADS with Parisi-Sourlas kind of supersymmetry. Now, there is some people who try to think about how such a supergravity will look like, but I don't think anybody has really studied it in ADS. Like, and then, like study branes in that theory or do something there, but I don't know of any. So I think, like somebody who studied, like, so, I think recently there was a paper by Tim Morris and Matthew Kellett. Like they tried to write down some supergravity theory with this kind of supersymmetry, but I think they were mainly just in some flat space thing. They were not putting it in ADS and so on. That's just a comment. So maybe like that should be done.
Yeah, this sounds like indeed what goes towards what Gautam was asking.
Any more questions? Well, if not, let's thank Slava for a wonderful and a very clear talk.
Thank you all for listening. It was a pleasure.
Thanks again, Slava. Thanks so much for taking the time. Hope to see you soon in Mumbai.
Me too. Bye all.
Bye.
Bye-bye. Bye.